Hey Jordan, how you doing?
I'm good, Dave. How are you doing?
Good. So I have so many questions because I find things like this pretty interesting, and I guess we should start by just having you guys introduce yourselves and your company, and then we can talk a little bit about some of the details.
Sure, absolutely. I'm Jordan Wines, and I'm one of the three founders, along with Peter and Rusty, who's not here, of Vector 35. We make Binary Ninja. That's what most people, I think, know us for. And we've been around the reverse engineering community, the vulnerability research community for a while now. I've done work for a defense contractor for several years, and just got to kind of play with bug finding and static and dynamic analysis, and founded Vector 35 to, one, make hackable video games, and two, more importantly, to build Binary Ninja, sort of a new program analysis tool. Now, Peter, I didn't cover his.
I'm Peter LaFosse, one of the other founders of Vector 35. I spent years working for the same defense contractor as Jordan. We worked together for almost 10 years. I ran the VR team there for many years, and had my background in finding vulnerabilities, zero-day vulnerabilities, and exploiting them. And I was always frustrated by using IDA. I always kind of felt like we need a better tool. We need something that's more featureful. I was always frustrated by the lack of kind of more advanced features that I wanted. And so that's one of the reasons why we wanted to build Binary Ninja.
What I think was fascinating that you guys described Binary Ninja as not a reverse engineering tool so much as a program analysis tool. And I've always I've come from the defense industrial base myself, but to me you guys were always really well known, and I think the wider world probably didn't know about you guys. But one thing that fascinates me is the very different philosophies that go into building and using all of these tools. And when you build a custom tool like this, it really does, it embeds your philosophy and where you see the future and all the things that you felt were missing from every other tool. And so that's one of the reasons I wanted to do this video, was so we could help understand some of those things. So I want to start by just asking you a couple questions so that everyone's on the exact same page, which is one of the features that you guys talk about a lot that you can compare to other tools, because obviously Ghidra and IDA are the other big tools in the space, is your intermediate language. So one question I would always come to you with if I was new to reverse engineering is, what is the value to me of the Binary Ninja intermediate language if I want to be like you?
Yeah, I think there's two parts to that. The first one is the implicit, why would you use intermediate languages at all? You have disassembly, and then you could punch into a decompiler and get some source code. What more would you want, right? The assembly is sort of the ground truth, and the source code is an easier to understand, higher level representation. But the funny thing is, all of these tools use intermediate languages internally. They just don't always expose it to you. And this makes complete sense, because a compiler goes through several intermediate languages on the way down to machine code. And so, of course, you would use the same in reverse. It's kind of a natural thing. But the key difference, I think, between the Binary Ninja ILs and the other products ILs are that, one, we from the very beginning set out to make them very, very accessible, and not just accessible from a design standpoint, so the APIs are available for them, but accessible to humans. You can look at it, you can read it. We valued that you could work directly with the ILs programmatically and also interactively. So you can disassemble a reverse engineer and analyze a program at the IL level. And we also have these tiered ILs. We have many different ILs internally. We're up to 7, I think, right now, depending on how you count it, and with more to come as we do higher levels of abstraction. And they have different properties. Some of them are useful for answering questions about where variables live on a stack. And then in others, the stack is gone because it's just abstracted. When you write your C, you just define variables, and the compiler puts stuff where it puts it. So we see there's a great value in different ILs for different purposes. And so that's like, I think one key difference there is that we have like many different ILs, which can make it a little more confusing, right? So we have to actually kind of like educate people and show them like, here's like why we use this IL, here's why you use this IL, here's a type of program analysis that happens best on this form of the IL. And I think these are questions that are really valuable because it lets you write code or write plugins to automate reverse engineering way more effectively. And you can do things you just can't do with other approaches.
Why wouldn't I just take like the Ghidra decompile and just write my analyzer right on top of that?
I mean, you could, and it would be in some ways better than disassembly, right? Because they have done a lot of analysis for you, but it's not a system designed for analysis. Like it's source code, so now you're going to have to take your Lex. So like all the same problems you have like in the source code standing software, you're going to have to apply to that. The other problem is that like C doesn't represent things that you care about. There are conditions. If I know a function is called with a particular range of values on one of the parameters because I've analyzed the whole course of the program, that's not something I can represent in C. Like C doesn't actually have the ability for me to inform the user about things that my program analysis system knows, whereas an IL can and should give you more information. I should have APIs to be able to query the state of the system at different points. And now, like you can make it so you can visualize the stuff in C, and that's useful and that's valuable because that's just what people know and they're used to it. But you shouldn't be like automating on top of that because now you're having to like build like source code parsers and scanners when you already have like right below that source code an intermediate language that is more amenable to analysis. Like you can write queries and walkers and things that will answer questions that you have, like find the bugs that you want to find. Like the whole point is like, are you finding more bugs? And if it's easier to find more bugs, then it's a better platform. And so I think that's the difference. Like source code, yeah, you can do it, but like why? You already had a better representation before you went all the way to source code.
When you write program analysis tools, are you writing them in Python? Because one of the things I always loved about Binary Ninja was that the Python API was sort of a first-class feature.
Yeah, so we focus on our Python interface a lot, but we actually build all the core functionality into the core in C++ for performance. And I think that we've tried to thread the needle of both accessibility of the API and also the performance you get out of it. Because program analysis is like inherently, there's a lot of computationally hard problems there. There's a lot of, especially for larger binaries. I mean, just look at like state space explosion of trying to analyze all possible paths through a program. Like you can't actually do that on any modern software. So you have to take a lot of shortcuts and cheat, and you can use concolic execution where like you try to like take some concrete paths from an emulator or a debugger, and then you apply that with other kind of analysis. And so there's all these ways that we're trying to like improve the performance of it. So we do have like the C++ core where we try to do all of the sort of heavy lifting. But then we write all of our like scripts and all of our like plugins on top of it. We tend to do them in Python too, because it's just easier to throw together a quick Python where the bulk of the work is carried out in the native library for performance reasons, but the higher level logic you can do in Python. So we think that's kind of a nice balance. And yeah, we put a lot of work into the Python API, so it's not just like you're calling directly into the same C++ API, and it just happens to be through Python, but you actually have Pythonic stuff. You have Python helpers and iterators and the things you would expect to be able to quickly write Python.
Do you have any examples of potential issues you would have if you're trying to build a plugin and you don't have access to this high-level IL?
Yeah, I mean, look at pretty much every project that has tried to kind of shoehorn some program analysis into IDA. They essentially have to bring along their own intermediate language representations that they're having to lift to. They have to bring along their own value set analysis, SSA transformations, all of that. It just doesn't exist in the normal IDA API, and so that's kind of the big issue there.
I was very glad that they was it last year? I think that they opened up their microcode implementation. I think, and they've obviously they've had an internal ILs for this, because that is right way to solve this. And so I'm looking forward to seeing if they continue to add on to those APIs as well. But again, I just think that IDA is a fantastic reverse engineering tool, right? It is. They've got a lot of breadth of support for architectures, and they put a lot of work into fixes and analysis paths and recognizing different compiler conventions, and they've got a great test database. Like, they've done a really good job for the industry, but I don't consider it a program analysis tool for exactly the reasons that Peter just mentioned, and that a lot of these sort of program analysis capabilities you sort of have to kind of bring alongside of it. So I think that there's a sort of different focus and perspective there.
What does it look like? So if I'm new to Binary Ninja, which, to be honest, I kind of am, what does some of this intermediate language look like, and what sorts of issues can I start to see with looking at it directly in C?
Yeah, so here, let's see, I'll pull up some random binaries. This is actually some malware sample that came out of a malware dump recently. I don't actually know what it's doing. I haven't even looked at it. I just pulled it up to show off a different feature earlier. But we've got the traditional flow graph, right, which everybody, I think, is familiar from IDA. They popularized the flow graph representation. But if I look into the IL levels, one of the things you'll notice is that the basic blocks are still there. It's still the same structure and shape. They're actually getting slightly smaller, though, if anything. There's actually less text in these, which makes sense. As you get more abstracted, you're going to lose details about the implementation, and it's going to be more, it's a variable now. It's not a register or a memory address. And then it's just going to be accesses of that variable and reason rights to the variable. And so you'll see that as we hit I to kind of flip through these. And so we went from 3 lines to 2 lines, and each of those lines got simpler kind of the more that we moved on in the basic block. I mean, this reads like pseudocode. There's a lot of people for whom C is just what they really, really want to see, is they really need to see decompiler. But a lot of people that ask for a decompiler, when I show them our medium level IL here, they're like, well, actually, that's a good enough high-level summary. I don't have to know a lot of the architectural details. Yeah, it's called EAX4, but that's just the variable name, and I can name it something else if I wanted. It's not. I'm not required to know any intricacies of the native instruction format, right? And that's the value you get of the IL, that you don't have to know exactly what every instruction does. You get a high-level summary of it, which again, you can take that all the way up to source code. But even if you don't, you've still got a useful summary that's not as tied up in the hardware.
But the real important, like, if I was doing program analysis, I can also use this IL and write my program analysis in sort of an architecture independent way, I assume.
Yeah, that's exactly right. And in fact, I think we published this video a couple weeks ago showing one of the plugins that we use at the training class that we give. We're doing down there at Infiltrate. Thank you for having us again. And this is a plugin. It was based on a plugin that FireEye did a blog post about how they resolved git proc adder dynamically loaded modules, right? So if you don't have as much useful information from your imports because it's not actually imported, it's just loaded, kind of hot loaded the functionality. And so we're like, oh, that's a great idea for a plugin. So we built that on our IL, and sort of for free, you'll notice we went from POSIX implementation there over to Windows. So we've got the Linux, Mac, FreeBSD function prototypes for those particular. In this case, we're looking at a Python, a compiled Python library that's loaded on the fly. Up to the Windows implementation, uses git proc adder versus DLSim. And so, like, other than the fact that we have to give the different function prototypes for each platform, there's nothing else in the code that's specific to Windows or to x86 even. It's literally just iterate over the IL, look for calls, look for writes to memory of the pointer for resolving those function pointers, and then we can annotate not only just like the name of the function in the comment, but we can actually go through and get those function prototypes throughout where they're referenced in the rest of the program. So yeah, you get that like for free with doing no extra work because you did it on the IL. And also it tends to be easier because the IL itself is sort of a simpler platform. You don't actually have to know, for example, a calling convention to know where the return address is going to go, or where the first argument is going to be. You can just ask where's the parameters for this function, what's the first parameter, and then the API handles that for you.
Types seem like one of those things that makes program analysis painful in nearly every way. How do you guys sort of think in your own head about types as you're building something like this?
It's a interesting question. So, we try to define our type system in as expressive a way as possible. People usually tend to think of the type system in terms of C, but C, honestly, the type system there isn't that expressive. Like as Jordan was saying, when you have a pointer, you don't necessarily know what the size of the data is that is pointed to by that pointer. If you have something like a tagged union, where you've got a type and then a set of unions that correspond to that type, that relationship between the type and which union member isn't explicit. And so when designing our type system, we wanted to keep all of these things in mind in this, as well as this aliasing stuff, pointer aliasing issues. We want to keep all those in mind as we're building out our type system. Not all of those things are currently in the product, but as we were working towards our next high-level IL, we're certainly thinking about adding those in.
So, I mean, just for people who've never done program analysis, I feel like you guys are such in the program analysis weeds that for you everything seems very like you just know all that stuff in your head. But what is pointer aliasing as a problem?
All right, so pointer aliasing is one of the most difficult problems to deal with in program analysis, and this really refers to the fact that if you are trying to do analysis of a single function and you have two pointers being passed in, it's really important to know what those two pointers are pointing at. If one is pointing to the stack and you have writes to that pointer, if you have too many writes to that pointer, then you're going to clobber some return addresses or some variables on the stack. If it's a pointer to the heap, you're going to have similar problems with the heap. If they point to each other, you then have this even more complicated relationship between the two pointers. So if they're pointing to each other, you write to pointer A and then you read from pointer B. You really want to know that those things are alias, so I can know that the value that's at B has changed. And the more and the better aliasing information you have, the better output you can have when it comes to lifting to higher levels of IL or even to decompilation or doing your value set analysis.
So I think some of these, you guys have been doing this for so many years, and it's just some of this understanding of what you did in the product is important, and then how do I build on top of this to solve my own problems that I thought was really exciting about all of your trainings. I'm always very excited to learn from people in the field what they see as the differences between how they approach a problem and how other people approach a problem. And so honestly, I'm real excited to have you guys at Infiltrate again, and I wanted to thank you guys for doing this little video for us, and then hopefully we'll do some more of these on other topics going forward.
That'd be great. Thanks for having us.
Thanks.